Okay. Okay. So our live stream has started. I'll just wait a couple minutes until it reaches 7:35 so that we can start. So yeah. Okay. Just gonna wait a little bit longer for it to reach our time slot. Dun, 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 dun. Okay. This is a really long minute. Okay. So it is now 7:35, so I'll start the presentation on material science. So as you probably know, material science is a totally, completely brand new event this year. It's new for this year, but it has been an event in the past, so there's probably gonna be like a vast minority that have done this or know about it before, but for the most part, all of you guys who are interested in this event are all starting on the same playing field. So, again, this is a lab event, like all the other ones, where there was a written part and a lab part. So, obviously, since this is new this year, I don't have any actual personal experience doing this, but this is just from all the information I've gathered on this. So, the lab part appears to be not related to the written part at all, like similar to chem lab. So it shouldn't matter if the certain partners don't finish at the same point. So from what I've gathered, this event is, while chem lab and forensics are basically like only chemistry events, material science is a mixture of physics and chemistry. Like many of the topics that they cover are actually part of physics. So actually, I would advise, if there's any like physics people, or if you know any physics people out there who want to try doing material science, I would actually advise for a partnership to be formed of someone who's really confident in chemistry and someone who's really confident in physics, because I think that will work the best. And you are allowed 5 pages of notes, similar to all the other chem events so far. Okay, so for parameters, obviously since the lab parts, safety and lab skills are very important, and basically the essence of this whole event is that you're being tested on different materials, hence material science, and their properties and applications. So yes, so I'll move on. Oh, and since I keep on forgetting to say this in the beginning, if there's any questions, I'll check them after I've gone through the whole presentation. If I don't get to your question, you can always email me with more. And yeah. Okay, so for content. Again, you see a long list of stuff that you should know. But so as a general breakdown, I'm just gonna go over the different parts that they have so far. So there's 3 on the rule manual, which I'm looking at right now. There are 3 main sections, or they've split up the test 3 main ways. The first one is general properties of material classes, physical characteristics, and manufacturing techniques, and natural occurrences in chemical composition, which is mostly chemistry with like other random things thrown in. The second part, which is the huge part, is material characterization techniques, or the visual physical traits, material selection for specific applications. That is like the physics part, and if you look at the rules manual, this is like the majority, or they use the most paper space on this section. And the last part is intermolecular forces and surface chemistry, hence the word chemistry. This is also a more chemistry centric part. Yes. So now I'll go a bit more in depth into each of these topics. So the first topics we're starting out with are the more physics ones. So the first thing you need to know is Young's modulus, which I'll just go a bit into each of these. Describes materials' resistance to linear strain. So obviously there's lots of formulas and equations for all of these that you will need to know and find out. And you need to be familiar with how to apply these equations, because again, like the chemistry one yesterday, it doesn't matter if you know the equations, but you have to know like how it works and when to apply it, because you can't just go around slapping like the Young's modulus on every problem you see, because that's not gonna work, and that's not right. Okay. So the next one is yield strength, which basically the yield strength is the force at which something begins to deform. Or the force that causes the changes to be unreversible. So like, if you imagine a spring, I'm just gonna use this as an example. A spring, when you stretch it out, like it deforms, but if you let it go, it'll return. But then there's a point where you stretch it so much that it's just gonna be broken and stuck there. So this is essentially the same concept, but when it's used in material science, it's usually applied to things like metals, and not like springs, like actual physical solid pieces. And part of this is the stress strain curve. Okay. The stress strain curve, which is basically like a graph that tells you like at which point is the deformity elastic, at which point does it not return back to its regular shape, and those kinds of things. So you should know how to read one of these, possibly create them. Again, like later in the resources I'll talk about practice tests, and like these tests, no one really knows what they're gonna be like, especially usually no one knows what it's gonna be like, because everyone who makes a test makes it a different way. But then especially for material science, since it's like a new, basically considered a new event, no one really knows what's gonna happen, so that's a bit hard. Okay, so the next one is creep rate, which if you look at the picture in the bottom right hand corner, that is a picture of the creep rate graph. So creep rate is the permanent deformation of material under constant load. So again, referring back to my spring example, it's the point at which, like, when you stretch a spring so much, it doesn't go back. And if you look at the on the graph in this PowerPoint, the middle one, the one that kind of looks like a cubic function, I don't know how else to describe it, that one is the ones they focus on the most, I would say, which tells you the primary, secondary, and tertiary, which you'll have to research more to find out exactly what that means. Okay, so next, surface area and volume. This is pretty self-explanatory. I'm sure all of you know how to find surface area of various prisms and objects, and also volume. And if you don't, go search out or ask a math teacher or whatever. And you will also need to know surface area to volume ratio, which is usually just a simple like division ratio. So that's not too hard. Okay, viscosity is one of the more chemistry ones, I would say. Like so far up to now, all of the concepts have been more physics related. But viscosity is the resistance flow. So if you think about maple syrup, I would describe that as viscous because it's not like water that pours really easily. And if you look at the top picture here in the top right corner, with all the arrows, that's basically showing a possible concept question that they might ask you, which in this picture it's showing that the liquid or substance in the middle of the channel has the highest velocity, while the ones on the sides have lower ones. So they might ask you, for example, to explain like, why this happens, which you should know. Hint. Yeah. The next one, returning back to physics concepts, is fracture toughness, which basically tells you how much stress you need to make an existing flaw bigger. So let's say, for example, okay, let's say you have a brick, and this brick has a crack. This is basically the amount of stress and force you have to put on it to make it worse. Um, Again, there's like a formula because essentially for all of the physics, I would say mostly for the physics concepts, there are formulas for all of them that you will need to know. They are very complicated, so I would not recommend trying to memorize them. Instead, just like put them on your note sheet. Um, yeah, and there's different types of fracture toughness, so you should know that too. Just saying. Okay. Again, another physics concept is fatigue limit. So this is the amount of stress required to cause a failure. Yeah. So as you can probably tell, like a lot of these concepts have to do like stress and strain and all that stuff. And again, this is like relating to the application part, because if you're gonna build a bridge or something, you want to know like how much stress can the material endure, like which will indicate how often you have to repair it. So I would say this material science, the event, is a much more applications and like real life centered, other than like chem lab, which is just asking you to answer a bunch of random made up questions and all that. So yeah. Another physics concepts, as you can see, there's a lot of physics concepts, is the shear modulus, which again there's another. It's basically a ratio, of like comparing the strains and stresses, and it helps measure how rigid it is. So like to describe a shear, this is a kind of strange example, but if you guys have really old textbooks where the binding is not very good, if you put your hand on the top and like move it right and left, the book will like shift a little, so it will look like a parallelogram at some points, and that's basically shear. Um, yeah. Okay. So the next one, Poisson's ratio, some weird French thing. Um, so it's basically a measure of how much it'll shrink or expand when you push it or pull it. So again, like, yeah, and this will usually be with like solid materials like metals. Um, and again, there's a formula for this, and there's since there's different types of strain, you can have multiple Poisson's ratio for one substance, which they might ask you. Um, okay, so the rest of these are, or most of the rest of these are more chemistry events. So for example, surface tension. I'm sure if any of you have taken chemistry, you know, or have some general knowledge, you'll know what surface tension is, which is, in an example, in this middle picture of this insect that is floating on water because of the surface tension. Um, so they might ask you to find surface tensions of different substances. They might ask you concept questions. In general, just be prepared for everything. Next one is contact angle. So, you know, um, so example, if you guys have ever put like a drop of water on like a piece of plastic or metal or something, it forms like a little dome, like a little droplet. So, um, the contact angle is basically where that liquid meets the solid surface. And note, it does not have to be a liquid, it can be other things as well. And this can determine the quote unquote wettability of a surface. So for example, um, if you guys have ever like, or like if you've ever cooked and like put oil in a pan, it doesn't just like turn into a puddle, it turns into like droplets. Um, so that would like indicate the wettability of a certain um surface. So yeah. Okay, so moving on to the last one, crystals. Um, the crystals is the majority of the chemistry part. So essentially all the chemistry part is just asking you about crystals. So there's different types of materials that they will test you on. Some common ones include ceramics, crystals, um, amorphous substances, polymers, metals, that kind of things. I would say the main ones would be ceramics, crystals, metals, and polymers. Yes. So make sure you know what those are and like specific characteristics of them that make them different from the other ones. So going more into crystals. Um, I'm sure you guys all have seen salt or some kind of crystal like quartz. Those are all crystals. So crystals are made of a basis or motive and a lattice. So the lattice is the structure and the basis or motive is what it's made out of. So um an example of lattice would just be like a square pattern, and a basis would be like red dots, or and a and that would be one crystal. But if you have a square structure with like blue dots, that would be a different crystal because the basis is different. Okay, there are no dots in chemistry and all that. This is just an example to let you know the concept. Okay, so for crystals, there are multiple crystal systems, which are basically like different structures that they want you to know. There are 7 crystal systems that you'll have to know, but the complicated part comes in that each crystal system has different lattices. And if you remember, I just talked about this. The lattice is um the structure, or like the organization. So for example, um if you guys know the molecular structure of salt, NaCl, it's literally like little cubes. So that would be an example of one crystal system, the cubic system. But however, there are 3 different lattices in the cubic system that all look different. And salt, the structure of NaCl salt, table salt, would be one of those. But there are multiple other ones as well. So you should be familiar with all those. And I would say, like, just to be on the safe side, know an example of each one. Especially since no one's really sure like what they'll test or how like nitpicky they'll be the questions. Okay. so there's different, what is it called? What is the word? Not perspectives. Like, the way that the molecules in the, or atoms or molecules in the crystal are packed are different. So I'll just give you, 2 examples. Unfortunately, I do not have pictures here. There is the simple cubic structure, which, again, as I just said, was NaCl. So if you picture that, or if you don't know what NaCl looks like molecularly, go to Google Images and search something up. And there's also the body-centered cubic structure, which is, let's see, it's, okay, the easiest way to describe this to someone who can't see it is NaCl with another atom right in the middle. So if you're confused, I would suggest you search out body-centered cubic structure, and there's multiple other ones that you should know as well. And there is at least one equation for the chemistry part, a lot better than the physics part, which is the atom packing factor, which again relates to like how atoms are organized and like the structure of crystals. So you should know that, because each system and lattice has a different APF, or atom packing factor. So you should be familiar with that. Let's see. Yes. Okay, so moving on. Okay, so these are some sample problems that I have here, for you guys to look at. Try them if you want. Hope you have fun. Okay, so for resources, some resources I would suggest would be the Science Olympiad official website. That's always good to like just get an overview, read the rule manual, or any like specific things. Sometimes they have like some notes on there too, so that's really nice. But that's just a really good like baseline place to start. Another website that I would recommend is the NDT Resource Center. I have no idea what NDT stands for. It's just some like national science thing, but they have pretty good resources and articles on a lot, especially the physics ones. They have a lot of those, which is good. For chemistry, I have not seen any of the chemistry information in any textbook that I have had or looked through. So for those, I would just recommend Google. Look on the rules manual, because that tells you specific parts of crystals that you would need to know, and I would suggest searching out, for example, what they say like surface chemistry, surface tension, they tell you ionic, covalent, crystalline, semi-crystalline, amorphous crystal structures, and things like that. So I would recommend just searching that up on Google and seeing what information you can find. Again, Google is a great source, even for physics. The physics aspects, just go on Google and it's great. YouTube is also great, especially if you don't fully understand a topic. Then I would advise you to go on YouTube and have some random guy like explain it to you, or maybe like material science is kind of an obscure region, but they should have, if you just search it up, the physics topics, there'll probably be some physics lecture talking about it, or if you search up the chemistry one, there'll probably be some chemistry one. And especially for chemistry, or even physics too, I would recommend going to Google Images and searching up lots of pictures of crystal structures, because even if you read it on some website, it helps a lot to see it visually and be able to understand it visually. So yeah, that would be good. And one physics work that I think is good is the Scioly physics textbook. I'm sorry, I have no idea who it's by, but literally on the front it just says physics and Scioly. So if you search that, I'm sure you'll find it. I believe I have the 6th edition, but again, this textbook is not required at all. You don't have to go out and buy it. You don't have to get the 6th edition either. You can just get anything. It's just something I think is helpful because it includes lots of practice problems, and it talks about a lot, if not, I don't think it discusses all of the physics concepts, but at least a majority it does go over. So I would recommend that. I was gonna say something else about physics, but I do not remember right now. Okay. I'll go check if there's any questions right now, and hopefully I'll remember that thing I was trying to talk about. Okay, so Carlton Kong. Okay, sorry, I shouldn't have said your name. The internet. Okay, so does 5 pages mean 5 front or back, or 5 sides only? Okay, so 5 pages. Okay, first of all, the 5 pages notes are not required, but if you're sane and want to do well, obviously you will use as much of it as you can. So 5 pages means 5 sheets of paper. Sorry, I should have clarified. It's 5 sheets of paper, so like 5 pieces of paper, front and back. And to maximize your space, I would recommend getting a good printer, or putting it in a printer that doesn't make it like super blurry and hard to see, making the margins as small as possible, and making the font as small as possible without having to use like a magnifying glass to read it. You will be allowed to use these notes for screening, so if you haven't started already, I would suggest you do. And obviously you can bring a calculator because like all of the problems require calculations. So I would suggest that. Okay, so now, okay, let's see if there's anything. What was that physics thing though? I was trying to remember. Oh, yes. Okay, I just remembered. Okay, so for content, where is it? For not all of these, on this PowerPoint and in this video, I included everything. Like, everything in the rule manual that you have to know. However, for state and national tournaments only, you need to know fracture toughness, Poisson's ratio, and the bulk modulus. Yes. So, wait. Scratch that. Fracture toughness, fatigue limit, shear modulus, Poisson's ratio, and bulk modulus. So, which means for invitationals and regionals, technically you should not have to know that. Again, unfortunately, no one knows what they're gonna throw at you. Sometimes they might bend the rules a bit and give you something that technically they're not supposed to. Hopefully that won't happen, but I would advise you to study for all of these, especially if you make it on a team. We are planning to go to states, so at states it says you'll have to know all of these. So I would much rather you just study everything now instead of scrambling to try to learn like 5 new concepts and their applications and how to use them in like April, because April is full of stress for AP tests and finals and projects. So I'd much rather you focus on school. Okay, so we're just about out of time, so I'll go check if there's any more questions really fast. But okay, it does not seem like there are any. So I'll end this now. Good luck on screening, which I think starts